Hello everyone and welcome back. Let's continue on with the second paper for the May-June 2023 series, specifically variant 2 for physics AS level. Now, before this we have gone through question 1 and question 2 separately so far. So do take a look at those questions first before we continue here onwards with question 3. So without any wait, let's begin. Now here's question 3 and let's read through it first. A block is pulled by a force X in a straight line along a rough horizontal surface as shown in figure 3.1. So here's the diagram. There's some velocity V, some forward force X, a total resistive force of 0.8 newtons. Assume that the total resistive force opposing the motion of the block is 0.8 newtons at all speeds of the block, so we assume it to be constant. The variation with time t of the magnitude of the force X is shown in figure 3.2. So here we have a graph. Now A part I tells us to define a force. Now here we have to take the actual definition of a force where we define it as the rate of change of momentum. Quite straightforward, right? Now let's move on to the next part. Determine the change in momentum of the block from time t equals to 0 to time t equals to 3 seconds. So if we look at the graph back here, from t equals to 0 to t equals to 3 seconds, we want to first see what force X is being applied. That would be up to this point. And since you have a difference of 1 Newton within 10 small boxes, that makes it to where each tiny box represents 0.1 newtons. So you have 1 here, 1.1, 1.2, 1.3, and this ends up being 1.4 newtons. So let's bring that here. So the force X that we're given from time t equals to 0 to time t equals to 3 seconds, that happens to be 1.4 newtons, right? And then the time duration given is from 0 to 3 seconds, which is just a 3-second interval, right? Now, this would have been enough information if it weren't for the total resistive force that's given here. We must remember that from 0 to 3 seconds, there is definitely that resistive force that's affecting the force X and its impact, right? And so, when we want to express the rate of change of momentum as force, we have to be precise in saying that this is not just any force, but it's the resultant force. And so, I have to first express this resultant force, which would be the forward driving force X minus the resistive force. Let me call it R. So we would get 1.4 minus 0.8, and this should be about 0.6 newtons. So now that we have our resultant force, we have the time interval as well. It's just a matter of rearranging this equation to get the change in momentum delta P, which would be the resultant force multiplied by the time interval. You get 0.6 times 3, and you should get in the end 1.8 kg meters per second. Right? Now let's move on to the next question. Describe and explain the motion of the block between time t equals to 3 seconds and time t equals to 6 seconds. So let's see. From 3 to 6, we can see that the resultant force had to drop from 1.4 to a new value that is 0.5, 0.6, 0.7, 0.8 newtons. So we have to first mention this part, that the force X decreases from the original 1.4 newtons down to 0.8 newtons. Now this new 0.8 newtons is special because it is actually equal to the total resistive force. So we have to mention this as well, that upon this decrease from 1.4 to 0.8 newtons, therefore the resultant force is not a non-zero value, but rather is the forward force minus the reverse force, the resistive force 0.8. So now the resultant force is actually 0. So we repeat, when we mention that x is decreasing from 1.4 to 0.8 newtons, therefore the resultant force is 0 now. And now we have to also explain the consequence of what's happening to the motion of the object now, right? In that case, what we should get, or we should in fact remind ourselves, and I'll write it down here, that when the resultant force of an object is 0, that basically means that object is no longer accelerating. And so the object has a new velocity that's now constant. So this is precisely what we'll mention here. So we repeat, x is decreasing from 1.4 to 0.8 newtons, therefore the resultant force is 0 now. And so the block will move with constant velocity. Either you could say constant velocity, or if you'd like, you could mention 0 acceleration. They should be equivalent, right? So with that out of the way, let's move to the next part. Force X produces a total power of 2 watts when moving the block between time t equals to 3 seconds and time t equals to 6 seconds. Calculate the distance moved by the block during this time interval. Alright, so this time what we want to relate is the force X with the power of this block moving. We're told that the power is 2 watts and this 2 watts is exerted when moving the block between time t equals to 3 seconds and time t equals to 6 seconds. Now, let's see. We can relate power with the time duration by actually writing out the formula for power. That is work done per unit time, or work done over whatever time duration that the force X is exerted. We're given the value of power, 2 watts. We're also given the time duration, which is from 3 seconds to 6 seconds. So that's basically a total duration of just an additional 3 seconds, right? So we can easily calculate the work done during this exertion of power between time t equals to 3 seconds to 6 seconds. We get power multiplied by time, 2 times 3, 6 joules. Now this is just the energy that's exerted. This is the, or more precisely, it's the work done by the force X, right? Now, we already know how much force is being exerted starting from 3 to 6 seconds. We've already figured that out to be 0.8 newtons, right? And we also remember that a regular definition of work done was what? Work done is force exerted times the distance covered in the direction of the force, right? In which case the force we know is force X times the distance that we wish to know. I'll just call it d. So we'll basically use this formula to our advantage. We have the energy of 6 joules. The force we know is 0.8 times the distance d. Therefore, the distance is simply 6 divided by 0.8. So now it's just a matter of plugging everything into your calculator, and what do you get? 6 divided by 0.8, and you should get 7.5 meters. Right? Alright, let's go to the next part. The block is at rest at time t equals to 0. On figure 3.3, sketch a graph to show the variation of the momentum of the block with time t from t equals to 0 to t equals to 6 seconds. Here, fortunately, numerical values are not required. Now, we already figured out two situations. That from 0 to 3 seconds, there was definitely some non-zero resultant force, and from 3 to 6 seconds, the resultant force had dropped to 0. Not only is the resultant so let's take it slow for a moment and look at the 0 to 3 second time interval first. So from 0 to 3 seconds, we've established that sure, the resultant force is non-zero, but we have also established that the resultant force is constant. That's not really a problem, or that's not something that I'm bringing up myself, because if we look back here, it's a horizontal line from 0 to 3 seconds, meaning that it's constant at 1.4 newtons. Now, when the resultant force is constant, And we know that the resultant force is rate of change of momentum. Considering how you have momentum on the y-axis and time on the x-axis, this is basically a change along the y-axis versus a change along the x-axis, which is nothing but the gradient in this case. So if the resultant force is constant from 0 to 3 seconds, that basically means the gradient should also be constant. The value doesn't really matter here, so you could just draw a straight line from 0 anywhere up to 3 seconds. Let's do it like this. And so it'll be a straight line, right? Now let's look at the situation from 3 to 6 seconds. Now from 3 to 6 seconds in this later half, we had recognized that the resultant force is 0 newtons now. When it's 0 newtons, we had also established that there is no acceleration, meaning velocity is constant. And if the velocity is constant along with the object's own mass being constant, that basically means momentum, which is a product of mass and velocity, that also stays constant. So after having attained some value of velocity, it's now going to stay constant, and so we'll show that with a horizontal line, which would basically be 0 gradient, right? So that does it for this entire question. So all of this was related to how we can relate resultant force with momentum and basically relate energy changes along with and how it can affect motion. Alright, so give this question a try yourself as well and see if you get your answers correct. Next time we'll move on to question 4. Thank you.